Look, if you are dropping marks on foundational SI unit calculations in your Cambridge Physics 9702 exams, you aren't just making small errors. You are actively risking your entire grade boundary. I am absolutely thrilled to have you here for this explainer, because today we're tearing down exactly what examiners are looking for. We're going to completely master SI units, base quantities, derived units, prefixes, and the principle of homogeneity. Now you might be thinking, I know this stuff. But this specific topic appears in every single examination series, literally every single one. So if you don't have a bulletproof strategy for these questions, you are leaving guaranteed marks on the table. We're skipping the fluff today and getting straight into the exact strategies that top-performing students use to secure maximum marks.
So what does this all mean? Why do top students, we're talking about students who know the physics inside and out, still lose marks on something as basic as SI units? Well, remember when NASA lost a $125 million Mars orbiter just because one team used English units and the other used metric? The painful reality is that ordinary revision just fails here. Most students treat SI units and prefixes as this basic, boring memorization task. They glance at the textbook, assume they'll figure it out on exam day, and move on. But because of this, even highly confident students absolutely bleed marks when they face complex past paper questions. Cambridge exams don't just test if you know a unit, they test if you possess a connected, conceptual understanding that you can transfer to completely unfamiliar contexts. The assessment framework prioritizes analytical depth over superficial breadth. If you just memorize, well, you fall right into the examiner's trap.
And this brilliantly illustrates our simple formula for top marks. Base quantities plus derived units plus homogeneity equals exam success. This is it. This is the foundational equation for your entire exam strategy. You need to intimately understand how fundamental base quantities combine to form derived units, and even more importantly, how the principle of homogeneity acts as your built-in mathematical lie detector to prove your equations are actually correct. Mastering this formula isn't just about passing, it's a total mindset shift. It's about learning to think exactly like a Cambridge examiner. When you apply this equation to your revision, you stop guessing and start systematically locking down every single available mark.
Okay, let's dive into this. Section 2. Core concepts and connections.
The theoretical architecture of these topics really rests on precise definitions, causal relationships, and integration with other syllabus areas. The principal examiner reports highlight something fascinating, actually. Candidates who explicitly reference cross-topic connections achieve significantly higher marks. You simply cannot treat SI units in isolation. They are literally the language connecting kinematics all the way to quantum physics. Now, what's really interesting here is the definition of homogeneity. Homogeneity is the principle that all terms in a physical equation must have the identical base SI units. But here is a critical examiner alert straight from the Cambridge Principal Examiner reports. Listen to this. Candidates consistently confuse key terminology. Examiners explicitly warn that students mix up base quantities with derived units, or they completely misunderstand how homogeneity actually applies to a multi-term equation. So the golden rule here, always define your terms before using them in extended responses. If a question asks you to use the principle of homogeneity to verify an equation, your very first step should be to mentally or even physically right there on the paper define what that means. You have to ground your analytical framework.
Scanning from pico all the way up to tera, you know these prefixes, right? Tera is 10 to the 12th, down to pico at 10 to the negative 12. But a simple calculation error here, like forgetting a negative sign and accidentally turning a microscopic distance into the size of a galaxy, completely destroys an otherwise perfect analytical framework. Systematic processing requires you to extract the relevant data and immediately convert it into standard base SI units before you even touch your core calculations. Actually, scratch that, it's before you even think about the core calculations. If you miss a pico in your initial data extraction, your subsequent scientific reasoning, no matter how brilliant it is, leads to a completely flawed conclusion.
All right, moving to Section 3, the method mark strategy.
This is where we shift our focus from what you know to how you show it. In Cambridge Physics, marks are heavily awarded for your structured reasoning, not just the final number at the bottom of the page. If you're just writing down a final numerical answer without showing the logical, structured process that got you there, you're instantly throwing away method marks. The assessment demands that you execute your analysis with totally clear working and present it in an appropriate format. In just a moment, I'm going to show you the hidden examiner clue that dictates how you structure that exact reasoning. It's this tiny detail in the wording that most students completely gloss over. But first, you need the framework that makes that clue absolutely obvious. Because honestly, you can't spot the examiner's trap if you don't have a reliable lens to view the problem through.
And here is that framework. This is the standardized sequence you must use when tackling any complex past paper problem. Step 1. Concept. Identify the key elements and the relevant physics principles. Step 2. Evidence and data. Extract the exact data given, making sure all those prefixes are converted to base SI units. Step 3. Scientific reasoning. Execute your analysis with crystal clear working, applying formulas and verifying results through homogeneity. And finally, Step 4. Examiner wording. Present your final answer using the correct terminology and proper headings dictated by the specific command words in the question. By following this concept-to-data flow, you are literally giving the examiner exactly what they need to award you maximum marks. You are making it impossible for them to penalize you.
Let's pivot now to Section 4, Top 3 Examiner Warnings.
We're going to adopt a spot-the-error mindset here, using insights straight from the principal examiner reports. These are the exact places where thousands of students lose their A-star grades every single year. Higher-order assessment objectives demand that we evaluate these common pitfalls so you don't repeat them. And get this, there are exactly 3 critical mistakes repeated in every single examination series. It's almost like clockwork. Recognizing these 3 specific errors is your ultimate defensive strategy in the exam room. Let's break them down.
First up, confusing cause and effect in SI units, base quantities, and derived units. Students often jumble up which base units combine to create a derived unit, and that leads to a whole cascade of errors. Second, forgetting to check format and presentation. This means ignoring strict conventions like proper headings, clear annotation, and using the wrong formats for your final answer. Third, answers are not specific to the context given. Evaluation of evidence quality requires you to identify limitations and assumptions specific to the exact scenario in the question, not just reciting some generic textbook definition. Here's a quick, powerful memory hack for you. Pause this explainer right now and create your own mnemonic using the first letters of key terms from these 3 warnings. Seriously, lock these into your memory right now so you automatically check for them during your exam.
Section 5. The high mark answer framework.
We've talked about the theory, the procedural framework, and those examiner warnings. Now it's time for a high-stakes practical application challenge. Notice the crumpled, flawed working on the left side. It completely ignores the principle of homogeneity. There's literally 0 check to see if the base units on both sides of the equation actually match. It uses an incorrect prefix format, probably missing a 10 to the negative 6 for a microconversion, and it entirely lacks scientific reasoning. It just jumps straight to a final incorrect number. Now look at the clean, structured flow on the right. That is a top-band answer. It features clear working, it explicitly defines the base units before calculating, it follows a beautiful, logical concept-to-data flow. This proves that presentation, appropriate terminology, and sticking to that procedural framework are everything. And hey, remember that examiner clue I mentioned earlier? Well, it's always hidden in the context of the question. If the question gives data in millimeters and milliseconds, the top band student spots that immediately and converts to base SI units in step 1. Meanwhile, the flawed answer rushes in, misses it, and completely loses the method marks.
And finally, Section 6, the timed writing system.
So, you now possess the foundational framework, but there is an invisible enemy waiting in the exam hall. Knowing the exact method means nothing if the exam clock beats you to the final mark. Exam timing pressure is the ultimate confidence shock. You can structure the absolute perfect concept to data flow, but if it takes you 15 minutes to answer a 4-mark question, are you really mastering the paper or is the paper mastering you? Solving this timing crisis is absolutely mandatory. That is exactly why our next explainer on the timed writing system is an essential next step for you. Subscribe to our YouTube channel, Ace the Exams at acetheexams_IGCE to excel in your Cambridge examinations, master the framework today, and I will see you in the next explainer to conquer the clock.